Hello everybody, and I hope you are fine. In the previous video I showed you how you can specify and estimate a one-factor CFA model using the graphical method in EQS. In this video I'm going to review the results of the analysis for this particular CFA model that are printed in EQS output file. So this is our CFA model. The factor is supervisory support with 5 items. Note that all the fixed parameters are in red color and the free parameters to be estimated are represented by asterisks. So let's go to the output file. Okay, this is the output file for this CFA model. The first section is program control information, and here you can see the content of the EQS input file, including the equations, variances, and all the other things. Then we have the path of the data file. Also note that we have 98 variables and 2324 cases in our data set, and our data is raw data. Then we have univariate statistics of the observed variables in our data set, which include mean, skewness, kurtosis, and standard deviation of the items. Then we have multivariate kurtosis statistic. This is Mardias coefficient and also its normalized version. So the important statistic in this section is normalized estimate of multivariate kurtosis, which is 71.79. And basically when this value is greater than 5, it is the indication of multivariate non-normality of the data. So in this example, our data is multivariate non-normal. After that, we have elliptical theory kurtosis estimates. So again, here we have two statistics. One of them is kappa and the other one is mean scaled univariate kurtosis. And this kappa is used for elliptical computation. Then we have case numbers with largest contribution to normalized multivariate kurtosis. And in other words, these cases are multivariate outliers. And also we have their estimates here. So the initial examination of these values show that this case, and this case are extreme outliers comparing with this case and this case, and we can consider removing these cases in the subsequent run of the analysis. Then we have sample covariance metrics, and after that you can see Bentler-Weeks structural representation. So we have 5 dependent variables in our model, and all of these dependent variables are observed variables. So V24, V25, V26, V27, and V28 will be our dependent variables. Also note that we have 6 independent variables. One of them is a factor, which is factor 1, and the others are error terms, including E24, E25, E26, E27, and E28. In addition, we have 10 free parameters to be estimated in this model. And here you can see the determinant of the input metrics as well. Note that these two lines are very important lines, and before you evaluate the results, you should make sure that you have these two lines in your output file. Otherwise, the results may not be trusted. And after that, you can see the correlations of parameter estimates. This is something that we requested when we were creating our input file. So these are the correlations of the parameter estimates. Then we have residual covariance metrics, and also it's a standardized version. So the residual covariance matrix shows the discrepancy between the sample covariance matrix that I showed you earlier, and also the model implied covariance matrix that I will show you soon. Also note that the interpretation of a standardized residual matrix is much easier, so we focus on this matrix for the purpose of interpretation. Okay, now for a good fit of the model to the data, we expect the residuals to be small and also evenly distributed in this standardized residual matrix. So large residuals associated with parameter estimates indicate their misspecifications in the model. Note that two averages of the standardized residuals are also printed below this matrix. So one of them is average absolute standardized residual that is based on all of the residuals in this matrix that you can see. And the other one is average of diagonal absolute standardized residual that is based on all of the statistics here excluding the diagonal elements. And basically this value, the second average, is more important, and when this value is very small, it can be seen as the indication of a good fit of the model to the data. Then you have the largest standardized residuals sorted here based on their size. Basically, by default, 20 residuals are displayed in this table, but given the fact that we only have 15 residuals, so all of them have been displayed here in this table. After that, you can see distribution of standardized residuals. So let me just highlight this section. Based on the statistics that you can see here, all the 100% of the residuals fall between minus 0.1 to 0.1, which means that all of these values are very small and very close to 0. So again, this is another indication of a good fit of the model to the data. And after that, you can see model implied covariance matrix. So this is the matrix that is compared with the sample covariance matrix, and the discrepancies will be displayed in the residual covariance matrix. Then you can see the goodness of fit summary for maximum likelihood method, and these include chi-square statistic here, degrees of freedom for the chi-square statistic, and also all of these fit indices. These are the fit indices that you can get from other softwares such as Amos. However, given the fact that our data were multivariate non-normal, we forget about all of these statistics and we will resort to their robust versions that are printed below. So forget about these fit statistics. And now here you can see reliability coefficients. So these are the reliability coefficients that by default are printed in the output file, and you can simply report all of these statistics in your publications. And now here you can see the robust fit statistics, including the Satora-Bentler chi-square statistic, and also its degrees of freedom, plus a lot of other fit indices such as NFI, NNFI, CFI, IFI, MFI, RMSEA, and also its confidence interval. So these are the correct fit indices that you can report even though the data is multivariate non-normal. Then after the robust fit indices, you can see the iterative summary, and here the program has converged in 4 iterations, and the convergence has been smooth as evidenced by the alpha values being 1 in these iterations. Okay, and here you can see the parameter estimates, including the factor loadings for V25, 26, 27, and 28, and also the variance for F1 and the variance of these error terms, E24, 27, 25, 26, 27, and 28. Note that the unstandardized estimates are listed under B, and the standardized estimates are printed under beta. So the standardized factor loading for V25 is 0.829. For V26, it is 0.820. and for V27 we have 0.899, and for V28 we have 0.914. Also note that the standard error and the Z statistics based on the traditional maximum likelihood method have been listed here. Given the fact that our data were not multivariate normal, so we just ignore these statistics and we will resort to these robust versions of standard error and Z statistic. So in case that you would like to report a standard error and Z statistics for factor loadings, you should consider reporting these robust statistics. Here also we have the variances for the only factor in our model and also the error terms. And again, we have a standard error and Z statistics for these variances, and we need to ignore these statistics and just resort to these robust standard error and Z statistics in case that you would like to report the significance of variances in your model. And finally, you can see the standardized solution. Again, here you can see the standardized factor loadings for the items and the R-square values. Okay, so that was all I wanted to share with you with respect to the output file for the one-factor CFA model in our example. And I hope you liked this video, and thanks for watching.